Hello, I'm Yang Hao. Today I will present our work LDP, Language-Driven Dual-Pixel Image Defocus Deblurring Network. Our work focus on defocus deblurring, which removes unwanted blur from defocused image. As shown in the figure, we restore a latent sharp image by deblurring process. When capturing a photo, the user adjusts the aperture size. In some scenarios, a wide aperture results in a higher quality image. For example, wide aperture increases the amount of light in a dark scene, improves shutter speed as well as reduces noise. However, a large aperture has a shallow depth of field which results in defocus blur. Since depth and defocus blur are correlated, defocus blur tends to be spatially variable. For example, the red and orange boxes in figure A have different degrees of blur. This makes defocus deblurring very challenging. For hard defocused image deblurring, recent works use blur maps to facilitate the removal of non-uniform blur. However, blur maps of real scenes are difficult to obtain. This makes it difficult to train blur map estimation models. Therefore, we query, can we design a network for unsupervised blur map estimation? Blur map is a quantization of the degree of blur in different regions, and we thought of using two new techniques to quantify the blur. Firstly, we thought of using the rich semantic knowledge of VLM to quantify the blur. Secondly, we thought of a new type of sensor, DP sensor, which are able to acquire two images in a single shot, and the relationship between these two images can quantify the defocus blur. CLIP is a typical VLM model. The zero-shot learning capability of CLIP is one of its outstanding advantages. However, using semantic knowledge from CLIP to handle low-level vision tasks is underexplored. Thus, an initial idea was born. Can we use CLIP's zero-shot learning ability to quantify blur? We first made a simple attempt by taking a blurry image as the text prompt and patched defocus blur image as the image input. As expected, CLIP is able to roughly distinguish between blurry and sharp. However, this is a noisy blur map. Therefore, we thought about the nature of the DP images and considered using it in the DP image. After VLM, we will briefly review the DP sensor. This is a novel image sensor designed by Canon, who used the image sensor for both image capture and phase detection autofocus. The DP sensor splits each photodiode of a conventional image sensor into two photodiodes, each of which records light intensity independently. Thus, the raw data recorded by photodiode L and photodiode R are saved individually and processed to obtain two images, named left view image and right view image. For blurred areas, the left and right views have a small disparity. For clear areas, there is no disparity between the left and right views. There have been several efforts to use DP sensors to facilitate defocus deblurring, which have proven to be effective. To input two images into the CLIP, which trained on monocular images, we designed a new DP-aware format. We concatenate the left and right views into a single image, and then query the similarity of the image to the difference-related prompt. However, our results are not satisfactory. Therefore, we ponder how to further utilize the properties of DP images. We thought about the symmetry of the image. As can be seen, the clear image has no disparity and the image remains symmetric after flip and concat. While the blurred image is asymmetric after flip and concat, that means symmetry can quantify the amount of DP image defocus blur. The observation inspired us to use CLIP to query the similarity between the flipped image and the symmetry-related prompt, such as a symmetrical image at the pixel level. The blur map obtained in this way is satisfactory. This is our two formats for generating blur maps. Blur and disparity are two related representations of the defocused region in a DP image. Can we combine the two representations? Based on this question, we combine these two formats, using prompt ensembling. As can be seen in the figure, the ensemble format obtains the most accurate blur map. This is our general framework. It contains three designs: a CLIP-based blur map estimation module, a blur prior attention module, and two blur map-based loss functions. We compare with state-of-the-art methods on three datasets. Quantitative results demonstrate that our method achieves state-of-the-art performance. Here, we provide some qualitative comparison on DP deblur dataset. Our method has the sharpest text edges in deblurred images. On the DP DSP dataset, our method obtained the best visual results. On our collected nighttime blurred images, our method still obtained the sharpest results. This shows that our method has good generalization ability. Thank you for watching.